Every time you call optimizer.step, PyTorch has already computed the gradient of the loss with respect to every weight in your network. That computation uses exactly one mathematical rule, the chain rule, applied recursively from the output layer backward to the input. Backpropagation is not a mysterious algorithm, it is the chain rule in disguise. Today, the power rule, product rule, quotient rule, chain rule, partial derivatives, and the gradient vector. By the end you will be able to derive the gradient of MSE loss, cross-entropy loss, and the one hidden layer network by hand. 7 rules cover nearly all derivatives in machine learning. Power rule: dx of x to the n equals n times x to the n minus 1. This gives us weight decay. The gradient of w squared is 2w, so L2 regularization adds 2 lambda w to every gradient. Constant rule: dx of any constant is 0, bias gradient contributions from constants vanish. Sum rule: dx of f plus g equals f prime plus g prime. Loss functions are often sums, so this lets us differentiate term by term. Product rule: dx of f times g equals f prime g plus f g prime, used for attention scores and proving the sigmoid derivative. Quotient rule: dx of f over g equals f prime g minus f g prime all over g squared, used in softmax differentiation. Essential derivatives: dx of e to the x is e to the x, dx of lane x is 1 over x, dx of sigmoid is sigma times 1 minus sigma, and dx of than is 1 minus than squared. The chain rule: if y equals f of g of x, then dy dx equals f prime of g of x times g prime of x. Outer derivative times inner derivative. Example: differentiate y equals the quantity 3x squared plus 1 all to the fifth. Outer function is u to the fifth, inner function is 3x squared plus 1. Outer derivative is 5u to the fourth. Inner derivative is 6x. Chain rule gives 5 times the quantity 3x squared plus 1, all to the fourth, times 6x, equals 30x times the quantity 3x squared plus 1 to the fourth. Now the connection to backprop. A neural network forward pass is a composition. Input goes through linear layer, then activation, then another linear layer, to the loss. The backward pass multiplies local derivatives. dl over dw equals dl over dar, times dar over dz, times dz over dw. That product of 3 terms is the chain rule applied to the network composition. Each layer computes one local derivative. Backprop chains them together. Partial derivatives extend differentiation to multi-variable functions. The partial of f with respect to x sub I means vary only x sub I, hold every other variable fixed, and take the ordinary derivative. The gradient vector of f is the column vector of all partial derivatives, partial f over x1, partial f over x2, all the way to partial f over xn. The gradient points in the direction of steepest ascent. Gradient descent subtracts the learning rate times the gradient to move toward a minimum. 2 key results. Gradient of mean squared error with respect to w is negative 2 over n times x transpose times the residual y minus w transpose x. Gradient of softmax cross-entropy with respect to log at z sub I is simply p sub I minus y sub I, prediction minus 1 hot label. The Jacobian matrix generalizes the gradient to vector-valued functions. J sub I j equals partial f sub I over partial x sub j. It appears in vector backprop when layer inputs and outputs are both vectors. 4 applications. 1. MSE gradient. L equals mean of y hat minus y squared. Power rule on the square gives 2 times the residual. Chain rule brings back 1. Divide by n for the mean. Result: gradient is 2 over n times the error, exactly what SGD subtracts. 2. Cross-entropy gradient. L equals negative sum of y sub I times log p sub I. Chain rule through softmax gives the clean result. Gradient of z sub I is p sub I minus y sub I. PyTorch f_entropy computes and returns this automatically. 3. Linear layer weight gradient. Z equals W times X plus B. Local Jacobian of Z with respect to W is X transpose. So gradient of L with respect to W is the upstream gradient delta, outer producted with X. Bias gradient is just delta. The constant derivative of the bias term is 1. 4. Adam optimizer. First moment m is exponential moving average of gradients. Second moment v is exponential moving average of squared gradients. The g squared uses the power rule. The bias-corrected update divides by the square root of v, adapting learning rates per parameter. 5 things cold. 1. Power rule. D dx x to n equals nx to n minus 1. 2. Chain rule. D dx f of g of x equals f prime of g of x times g prime of x. 3. Product rule. D dx f times g equals f prime g plus f g prime. 4. Partial derivative. Vary one variable, hold others fixed. 5. Gradient is the vector of all partials, same shape as parameters. Exercise. Build a 2-layer network in PyTorch. Y equals relu of W2 times relu of W1 times X. Compute the gradients by hand using the chain rule for each layer. Then run backward and compare W1, grad and W2, grad to your hand computation. You now understand the mathematics that runs inside every training loop. The chain rule is not abstract calculus. It is the live code path in Torch. Autograd. When you call loss backward, Python calls the chain rule on the computation graph, multiplying local Jacobians from output to input. Partial derivatives make gradient descent possible. By computing each dimension independently, we can handle networks with hundreds of millions of parameters. Video 20 goes deeper, the Hessian, saddle points, and second-order optimization methods. Subscribe so Video 20 is ready. Post your answer to dy over dw for sigmoid of w times x in the comments. See you in Video 20.